In this video, we will look at two rules that will help us to algebraically evaluate some limits. First, let's start off with some limit notation. We can express the limiting value of any function, call it f, by this notation, and we would read this as the limit as x approaches infinity of the function f of x is equal to L. What this means is that the values of our function f approach this number, whatever it is, L, as the x values approach infinity, or as x gets bigger and bigger. This number L is called the limit. Our first rule says that for any number, let's just call it a, where a is between 0 and 1, so it has to be a positive number but a small decimal, the limit of that number to the x power as x approaches infinity is 0. And so this is the notation we'd have, and it would read pretty much the same. The limit as x approaches infinity of a to the x is equal to 0. And this is true as long as a is between 0 and 1. Let's look at an example. Okay, this is the limit as x approaches infinity of the function 0.35 to the x power. Now this matches up pretty much with the format of our formula. We have a to the x, and in this case we have 0.35 to the x power. Okay, so that means the a is this point, this 0.35. And if we look at 0.35, that's definitely between 0 and 1. So this fits within that rule. And we always have to check that if we're going to use this rule. What that tells me is that the limit as x approaches infinity of 0.35 to the x power is equal to 0. So this limit is equal to 0. Here's another example. This is the limit as x approaches infinity of the function 1.2 plus 0.107 to the x power. So this 1.2, it does not have an x term on it, so this is just a constant term. It will always stay 1.2 to the x power. So this is always equal to 1.2. Doesn't matter if x gets big or small. This part here, if we look at 0.107, that's definitely, again, a number between 0 and 1, and it's raised to the x power. So by our rule, if we look at the limit as x approaches infinity, then this limit is equal to 1.2, since the 1.2 is a constant, plus we know the 0.107 to the x power by our rule is going to turn into a 0. So the final value of this limit is just 1.2. Let's look at the second rule. It says for any number, let's call it n, where n is positive, the limit of 1 over x to the nth power, again as x approaches infinity, is 0. So our notation, again if we read it through, would be the same. The limit as x approaches infinity of 1 over x to the nth power is equal to 0. And again, that's as long as n is positive. Let's look at an example. We have the limit as x approaches infinity of the function 5 over x cubed. We can actually rewrite this as the limit as x approaches infinity of 5 times 1 over x cubed. So now This 1 over x cubed looks kind of like that rule that we had. The n is the 3, so that's positive. So if we know that x goes to infinity, what happens to this whole fraction here? It's going to become a 0. So that means this limit, if we let x go to infinity, this 5 is not affected by that. So this 5 will stay the same. And it's going to be 5 times 1 over x to the third, which is going to become a 0. And so the limit for this function is 0. Here's a second example. The limit as x approaches infinity of the function 14 minus 7 over x squared. Now again, this 14 is just a constant. It will always be equal to 14. And this looks sort of like the rule that we have. It's just it has a 7 up there. So what we can do is we can rewrite that the same we did over here. We have the limit as x approaches infinity of 14 minus, well, I want it to look like 1 over x squared. So we can pull that 7 out front, and we'll have 1 over x squared. And again, I know the 14 is just a constant. There's no x, so it will not be affected by x going to infinity. So, and same thing with the 7. So only this 1 over x squared, will go to 0. So this here will go to 0. So what we're left with is 14 minus 7 times 0, which is just 14. So the limiting value of this function as x goes to infinity is 14. Now let's look at one more example. The limit as x approaches infinity of the rational function 2x plus 3 divided by 5x minus 4. Now if we look at this, we don't have an a to the x power in any of these 4 terms. This is 2 to the x, not 2 to the x power, it's 2x. This is 5x, not 5 to the x power. So it doesn't fit rule 1. And if we look at it in terms of rule 2, we always need it to be 1 over x, and that's not what we have. We have 2 times x. So how do we go about getting it to fit to one of our rules? Particularly, how do we get it to match up with rule number 2? There's a little trick that we need to do. You can take any function, any expression, and multiply it by 1. But the thing is, 1 can look like many things. 1 comes in many different formats. So what do we want it to look like this time? As long as I can have a fraction where the numerator and the denominator is the same, then this whole fraction actually is equal to 1, and so we're multiplying by 1, and that doesn't change the value of our formula. What I want to do is multiply something through the numerator to cancel this x out. So to cancel that x, I have to multiply by 1 over x. That's going to cancel this x out if I multiply that through. Now, if remember, whatever you do in the numerator, you also have to do in the denominator. So I'm going to multiply 1 over x through the denominator as well. And when we multiply this, it has to get distributed. So this is going to look like, again, we still have to do the limit. We haven't done that yet, so we need the notation. This is the limit. If I take 2 to the x times 1 over x, the x's cancel, and we're just left with 2. If I take 3 times 1 over x, well, we're just left with 3 times 1 over x. In the denominator, we take 5x times 1 over x. The x's cancel, and so you're just left with a 5. It's going to be minus. We take the minus 4 times 1 over x. We're going to have minus 4 times 1 over x. Now here's where the limit comes in. We now have this 1 over x expression. as x goes to infinity, these 1 over x fractions all turn into zeros. So this is going to turn into, again, as x goes to infinity, as we evaluate the limit, the 2 doesn't change, it's just a constant. The 3 doesn't change, it's just a constant. But that 1 over x turns into a 0. Same thing in the denominator. The 5 doesn't change, the minus 4 doesn't change, only the 1 over x, which turns into a 0. Which, if we multiply that, 3 times 0 is 0. So in the numerator, you're just left with a 2, and in the denominator, you're just left with a 5. So the limiting value, as x goes to infinity, of this function turns out to be just 2/5.